Problem number 11 asks, what is the value of the shares Samantha owns? And that is a classic part over whole type proportional setup. Okay, so we're going to look at the part over the whole. And what you want to do with this one is recognize that there's really information with regards to the shares, and there's information with regards to the dollar amount. Now, with regards to the shares, we're interested in Samantha's, the value of the shares that Samantha owns. So I'm actually going to write a little s here with a little parentheses because that's the part that we're specifically interested in, and S stands for Samantha in this case. And we want to get clear that Samantha has how many shares? Looks like it's 70 shares. 70 shares out of how many total shares? Well, that would be a matter of adding the amount of shares up. It looks like it would be 70 plus 50, which is 120, plus 40, which is 160. So apparently there's 160 total shares. We also know that the combined value of all of that is 6,880. So you could go ahead and represent that monetary situation over here. And the quote unquote whole amount with regards to the monetary situation is 6,880. And we're looking for, okay, well, what is the worth of Samantha's 70 shares? So that would be X right here. And in fact, we'll actually write S for Samantha. Why not? So that's the setup. And at this point, most of you watching probably know how to cross multiply. Now, I would actually advise before cross multiplying, cancel these zeros out, also known as divide 70 and 160 both by 10 to reduce the fraction, because that'll make your life easier. So cross multiplying 16 times s, that's obviously going to be 16s. Now, by the way, be careful when you're using s because that does look like a 5. Okay, so just remember that's an s right there. So it's going to be 16s equals 7 times 6880, and that is 48160. And then dividing both sides by 16 would give us s equals, obviously these cancel, s equals 3010. Okay, now when I write the numbers, I don't really like to think about where the comma would go right away, but I'm going to put them in now. So that's 48,160, and that's 3010. So it is for that reason that the answer is C. Now, another way of having gone about this is to take, the total, monetary amount that all the shares equal, and then divide that by 160 total shares. Then you would find out how much each share is, and then you could multiply that by 70. Now, ultimately, that is what we did here, okay? So this is sort of a way of cutting to the chase. However, in the absence of feeling confident with this kind of proportional, fraction over here equals a fraction over there, in the absence of this or having confidence in this kind of setup, you could have done that. You could have found out how much is each share worth, and then just simply multiply that by 70, and then you get the same number. Problem number 26 is obviously a probability problem, and it's a little bit different, though. This is kind of a nice example of how the standardized tests, such as the ACT, can give you these sort of creative variations of what would otherwise be a normal probability problem. What they say here, or what they're asking, is how many additional red marbles must be added to the 42 marbles already in the bag so the probability of randomly drawing a red marble is 3/5. Now, some of you might be having an instinct that says that you should probably find out, well, okay, I understand what the goal is, but how many, or what's the probability of pulling a red marble now? Okay, what's the probability of pulling a red marble now? Now, probability is always the desired outcome over the possible outcome. Okay, now the word desired is kind of weird. It means when we say the desired, what we're really saying is like the specific outcome that we're analyzing, as opposed to all possible outcomes. So we could at least find out like what is the probability of pulling out a red marble now? Well, there's 16 red marbles in there, and there are what is it? 42 marbles in general. Okay. So that tells us, what the probability of pulling a red marble is now. It's 16 red marbles in a bag full of 42 marbles. Now, so once again, the question is how many additional red marbles must be added to the 42 marbles already in the bag so the probability of randomly drawing a red marble is 3/5. So in other words, we're going to take this scenario where there's 16 red marbles in a bag full of 42 marbles, and we're actually going to add a certain amount of these to the bag. So we're going to call the amount that we're adding X. So what I'm going to do is, this is not equals, but an arrow that represents the new situation. Okay, so I'll even write new situation. And the new situation is we have 16 red marbles in the bag now, but we're going to be adding a certain amount. Let's call that X, right? But when we add X red marbles to the bag, well, we're adding it to the total amount of marbles, aren't we? So down below, you also have to write 42 plus X. Okay, if we're adding X red marbles into the bag, well, that's going to be X marbles in general in the bag, right? And this denominator has to do with how many marbles in general are in the bag. So this is a nice expression that represents the new situation. And what we want to do is we'll want to force that to equal 3/5. Okay, we want to force that to equal 3/5. Okay, because that's the sort of target probability. And one way of looking at this is we're really saying what value of X would cause the probability in the final analysis to become 3 red marbles for every 5 general marbles. Okay, so that's what we have to do, and we would cross multiply. So 5 times 16 plus X would give us 80 plus 5X. And 3 times the quantity of 42 plus X would give us 126 plus 3X. Now, I'm a big fan of having the X term in an equation be positive as soon as possible. So what I'm going to do is subtract 3X from both sides to keep the X term positive. That would result in 80 plus 2X equals 126. And most of you sort of know what to do from here, I'm sure. We'd be subtracting 80 from both sides now. And by the way, if you don't know what to do, that's fine. Now you're going to see what to do. I definitely want to get the term that has X in it by itself. That's the idea. And the term that has X in it is 2X. So we want to get that by itself. We end up with that. And then when we divide both sides by 2, I'm not going to write that. I'm just going to say dividing both sides by 2, we're going to end up with X equals 23. And that is the answer, and that is G. Problem number 32 requires an understanding of what it means to reflect an object across the y-axis. Many students watching might be a little bit more used to reflecting across the x-axis because maybe they just finished learning about parabolas and things like that, where it's a bit more common to reflect across the x-axis and the y-axis, but it is nonetheless true that you can reflect across the y-axis, and that is something that happens. So here is the problem. And what is it? A, B, C, D. It's like that. A, B, C, D. Now, the problem asks parallelogram ABCD will be reflected over the y-axis. What will be the coordinates of the image of A? Okay, so where it is now is called the pre-image. Where it ends up after the transformation is called the image. So it's kind of a weird thing in, about math language, we could say. The fact that where this point is now is called the pre-image. Right? So now means pre-image, and where it ends up, we call that the image. Okay, so don't be thrown off by that. Ultimately, they want the coordinates of A after the transformation. Now, seeing as how we're only concerning ourselves with point A in this problem, I'm going to just write those coordinates, okay? So as it stands now, point A is most definitely at -1, 1. But then when you think about it, well, let's think about what that means. I mean, what that means is the following. Now, what that means is that it is, and this is not drawn to scale, it's 1 up and -1 over. I mean, that's what it means, right? So again, not drawn to scale, but I mean, that's basically what they're saying when they say, oh, the coordinates are -1, 1. It means that it's -1 over and 1 up. So when we reflect it across this y-axis, it's almost like treating the y-axis like it's a mirror. Let's make it a green mirror. Okay, it's a green dotted line mirror. Now imagine that's the surface of a mirror. If it's 1 unit in that direction away from the mirror, it's going to be 1 unit in this direction away from the surface of the mirror in order to have that perfect reflection. Okay, so I would actually suggest a relatively visual approach to this. Now, there is like this algorithm that says, when you reflect across the y-axis, keep the y coordinate the same, but change the sign of the x coordinate. I mean, that could be useful, but the problem with that is you have to like memorize that, and memorizing those little algorithms is annoying. And if you forget it, I mean, you kind of, you know, that will hurt you, okay, if you forget it. So I'd rather rely on the sort of visual approach where you actually see the y-axis as a mirror and just be like, okay, if this was a mirror, well, what would happen in the reflection? The reflection would be the same distance away. You know how when you put your hand closer and closer to a mirror, the reflection doesn't like quote unquote touch your hand until you touch the mirror. And the further away you bring your hand from the mirror, the further back the reflection is going to go, right? So you want that perfect symmetry here, okay? I think you guys get the point. Either way, the coordinates 1, 1. And that is answer J. That's how you do that one. Problem number 34 asks, given that the school accepted 630 students, how many applicants were not accepted? The bottom line is, if we knew how many total students we were dealing with, we could subtract 630 from that number, and then we would have the total number of applicants who were not accepted. So I'm going to write that down. I'm going to write total students minus accepted students. That would give us the number of non-accepted students, kind of a weird word. Okay, so non-accepted students. Well, we already have the amount of accepted students. So what I'm going to do is I'm going to replace this with a t just to sort of save time. And it's going to be t minus the amount of accepted students. Now we know that 630 students have been accepted. And our goal is to find out, well, what is this question mark here? So obviously, it would be nice to know what T is. It would be nice to know what the total amount of students there are. So the question is, how do you find that out? Well, you find that out by setting up a proportion, okay? Now, apparently, 2 out of every 7 applicants are accepted, okay? So this is a part over a whole, okay? And what the whole represents is the total amount of students that we're dealing with, and what the part represents is the accepted students. I'll do a little A there in parentheses. Accepted students. So there's 2 accepted students for every 7 students in general. Now, they told us that the amount of accepted students in reality is 630. So you can set this ratio equal to 630, and it would be 630 over the total amount of students, and that's T. We'll just keep using T. So this represents the proportion of accepted students to general students, and this represents the reality, like the actual numbers, 630 literal accepted students, and therefore the T underneath would give us the literal amount of students in general. Cross multiplication would give us 2T equals 7 times 630, which is 4410. And then dividing both sides by 2 would give us 2205. So T equals 2,205. And, you want to just make sure that you remember the final goal is to figure out what is T minus 630, and that would be 2,205 minus 630, and that turns out to be 1575, and that is the answer right there, and that corresponds with answer choice K. Many people are used to adding fractions and finding common denominators. Maybe it's the case, however, that many of you are not as used to finding common denominators when you have variables in the denominator. Okay, so clearly the question is asking what is 4/5 plus 7 over x? And, there's this sort of annoying situation where we have a variable for a denominator. So I'm going to cut to the chase right now about what you should do when you have a variable in the denominator. Um, I'm at least going to give you something that will work every single time. Now, once you do it, you might have to do some simplification after, but this is something that at least would move you in the right direction, okay? Now, If you have a variable in a denominator and you have some other denominator, and you're trying to find the common denominator, it's pretty easy. You just add or multiply, I should say, the denominators, and that would give you the LCD, also known as the least common denominator. You just multiply them. So, seeing as how I already know that my new denominator is going to be 5x, I'm just going to write 5x in the denominator because I know that that's what it's going to be. And then what you do is you take the one denominator in one of the fractions and multiply it times the numerator in the other fraction. And then you take another denominator in the other fraction and multiply it times the numerator in the other fraction. So this would turn into this scenario. That will work every time. Now, it's the case that you might have to simplify things after that. For example, if that was a 5x, then you'd have to factor out a 5, and that would become 7. This would simply become x, and then the 5's would cancel here. Turns out that there's no simplifying that needs to be done. So we're good to go with these. And it turns out that's the answer. Actually, it's E. Some of you might want practice with that kind of thing, and I understand that. So here's some practice before we move on. Add these right now and see what you get. Go ahead, pause the video right now. Add it up, see what you get. And I'm going to give you the answer soon, so pause the video. Okay, so hopefully you pause the video, and ultimately the answer will be 21x, 9x plus 70, and divisible by 3. Are these things divisible by 3? Let's take a look. No, yeah, that is the final simplified result of this. There's no GCF here that I could take out. Can't take out 9, can't take out 3 up here. So there's no simplification that we could do from there. So that's the answer. Hopefully you got that. Hopefully you are now a master at this situation. Just do be on the lookout for any opportunities to factor out a GCF and then make cancellations just in case, okay? So that's how you do problem number 37. It is E. Problem number 40 says, after constructing the table, it was discovered that the student status of 15 residents who replied that they approved had been incorrectly classified as non-students. So in other words, 15 of the people, in this row turned out to be students. Okay, so let's see. After correcting the errors, exactly 60% of the college students had replied that they approved. To the nearest 1%, what percent of high school students replied that they approved? Okay, so here's the original table they gave you. Now, I want to just look at the big picture. And the big picture is that there's something that happened. There was the original analysis, of which this table symbolizes or communicates. And then there's the analysis that we could do after making the correction, okay? So what we're going to do is we're going to I'm going to make a table representing both situations and also representing the total amount of high school, college, and non-student people there are just in general, okay? Now, really, we're only looking at the column for approval, okay? So when I recreate some tables in a moment, I want to make it clear that this question only really has to do with approval. So in a way, we can sort of not bother analyzing too specifically what's happening in these columns. although we do need the totals to be taken into account. So I'm going to make some tables right now, and you will see what I mean. So here are two new tables that just sort of highlight aspects of not only this table, but what happens after the correction. Now here's before the correction. It's the same column here, high school, college, non-students in total. And we have, how many approved? We have 30, 14, 85, and 129. So that all lines up perfectly here. One thing I just wanted to highlight here is the total students just in general, because when it comes to high school students, 30 plus 4 plus 11, well, that's 45. When it comes to college students, 14 plus 10 plus 6, that's 30. When it comes to non-students, it's 85 plus 353 plus 47, well, that's going to be 485. And we don't really need this number here, but it turns out there's 560 total students. So just being thorough with that. Now, you might be wondering, well, why am I figuring out the totals? Well, at the end of the day, this problem has to do with percentages. For example, they mention 60% of college students, right? Well, in order to figure out a percent of college students, you need to know how many college students you're dealing with in the first place, okay? Now, keep in mind, this is before the correction. What the problem is saying is that they realized after making the original analysis that this 85 is incorrect. There's actually 15 people in this group of 85 people turned out to be students. This is the non-student row. According to the problem, 15 people out of this 85 people turned out to be students. So we need to subtract 15 from there. So what we're going to do is we're going to represent the changes over here. So 85 minus 15, clearly that will be 70. Okay, so 70 non-students approve. Now, the thing is we know that we're adding 15 total students to these two numbers, but we don't know how many students we're adding to 14 specifically, and we don't know how many students we're adding to 30 specifically. So we're going to need two separate variables to represent that. And I'm going to say, let's just say that it would be 14 plus x, and then we'll say 30 plus y. And let's keep in mind that x plus y is 15, because that's going to be a total of 15 students that's being added to the first two, to the high school approving students and to the approving college students, right? So again, we don't know what x is, we don't know what y is, but we know that when we add them up, we're going to get 15. Okay, now that's important. Let's see what else. Total students. It's going to be a good idea to figure out, okay, well, if we're going to be analyzing the percent of high school students who approve, things like that, then we're going to need to know the total students. Well, before this change, we made this correction. Before this correction, there were a total of 45 high school students, but now it's going to be 45 plus y. And down here, it's going to be 30 plus x. And the reason for that is because there used to be 30 total college students. So the new total college students is 30 plus x. And then over here, it's going to be 560 minus the 15, right? So 560 minus 15, well, that would be 545. And at the end of the day, they want, let's see, to the nearest 1%, what percent of high school students replied that they approve. So we're really interested in this percent approval here, okay? So that's ultimately what we're trying to find. They give us a clue because basically after the correction, they say that the college students are such that exactly 60% of the college students had replied that they approve. So in other words, this number, whatever this turns out to be, I mean, obviously we don't know what x is, but whatever this number is, that's 60% of the total college students. So after having made the table, it's a little bit easier to see what needs to be done now. So we know that 14 plus x of, 30 plus x, this total amount of college students, well, that's going to be 60%. So we could totally set up a proportion. And in doing so, we could figure out what x is. Now, if we figure out what x is, it's going to be easy to find out what y is because x plus y equals 15. And then once we know what y is, we could very easily see what percent of the high school students say that they approve after the correction. So let's go on that first mission of figuring out what y is. I'm going to take the approach of analyzing the part over the whole. Okay, there's multiple ways of doing percentages. You can think of it as is over of. There's ways of translating, um, you know, questions pertaining to percentages into algebraic equations. But what we're going to do here is just focus on the simple part over whole phenomenon. Okay, and what I mean by that is, bottom line is, apparently 14 plus X college students approve, and that is 14 plus X out of a total of 30 plus X. So what we could do is we could set up a proportion. So it's 14 plus X is the part, and then that's out of 30 plus X, which is the whole, and that's really equal to 60%. Now 60% is really 60 out of 100, so that's one way of thinking about it. Turns out that this reduces to 3/5. I would advise that to make your life easier. Cross multiplying, we of course would have to distribute the 5 into this entire quantity. We'd have to distribute the 3 into this entire quantity, and that's going to end up giving you, let's see, that's going to end up giving you 70 plus 5x, and then we're going to have 90 plus 3x. Just to save time and room, what I'm going to do is immediately subtract 3x from both sides, and I'm also going to subtract 70 from both sides. What that gives us is 2x equals 20, and then we would very quickly see that x equals 10. Once we know that x equals 10, we then know that this is really 24 and this is really 40, and that would give us the 60%. And in fact, I should really just write that. Why not? Because that's given in the problem, right? So they actually tell us that in the problem, 60% college students after the correction approve, okay? So therefore, if x is 10, then we can very clearly see that y is going to be 5, okay? So I'll just kind of write 10 plus y equals 15, and then I'll just make that note here that y clearly equals 5. Now, y is the number that we added to the high school, the approving high school students, okay? And of course, y is also the number that we added after the correction to the total high school students, okay? So that's 5. So let's just make the mental note now that if y is 5, well, this is really 35 approving high school students, and this is really 50 total high school students. We're going to make a little demarcation line here, and we're going to work out the last home stretch of the problem here. So really, there are 35 approving high school students out of a total of 50 total high school students. And that turns out to be 70%. Now, there's multiple ways of doing that, multiple ways of recognizing that this is 70%. One way of recognizing it is you could just take the part, which is 35, and divide it by the whole. That would have given you 0.7, which is 70%. You could also realize that, oh, well, this denominator, in order to turn it into 100, all I have to do is multiply it by 2. And of course, I have to do it to the top as well. And then I would have 70 over 100, and that is 70%. So I'm just going to write 70%. Now, that is the answer, and that is H. Now, do you have to make all these charts and all that? No, right? But you don't have to. It does make it easier, right? It does make it easier. And at the very least, you have to be thinking along these lines. You have to be thinking about, okay, first of all, we're only really paying attention to the approval column, okay? We're also only really paying attention to, you know, what happens, the percentage that happens after the correction. Now, in order to know the percentage, you also need to know the total amount of students in each of these rows, right? That's something that's not given in the original table. So it was really on you to know that, okay, somewhere along the line, I'm going to have to understand how many total high school students there are in general, how many total college students there are in general, and so on. That way I could sort of understand what the percentages are pointing to, because they gave us 60% of college students approving college students. Obviously, that's going to be 60% of the total amount of college students. Anyway, I think you get the idea. The answer is H. That's how you do problem number 40. Problem number 48 requires you to remember how to classify triangles. There's at least two different ways of classifying triangles. One is by the side lengths, and another is by the angle measures. We're going to make a little table that represents all that information now. So this rudimentary table sort of highlights exactly how to classify triangles by either angles or side lengths. So quick review, if all the interior angles are acute, that is an acute triangle. That might look something like this. If one interior angle is obtuse, it's an obtuse triangle, so that might look something like that. If one interior angle is right, then it's a right triangle. That might look something like that. Side lengths. All side lengths are equal. That's equilateral triangle. That might look something like this, or it does look something like that, where all the side lengths are equal. Two side lengths are equal. That would be an isosceles triangle. That would look something like that, where those two are equal to each other, and no side lengths are equal. That might look something like that, where that's clearly different. These three side lengths are clearly different. So, and it's the case that you could have combinations of these two different, classifications, and that is sort of what problem number 48 is hinting at. So the bottom line is the side lengths of a certain triangle, according to problem number 48, are 4, 5, and 7. So we already know that it is scalene. Okay, we already know it's scalene because the side lengths are all different. And therefore, we've already narrowed our answer choices down to F, G, and H, which is really nice. Okay, so we've already narrowed the answer choices, but the question is it acute, obtuse, or a right triangle? Well, there is a test that you can use, and the test is as follows. Typically, if it's a right triangle, we know that it would be a squared plus b squared equals c squared, because that is the Pythagorean theorem. And let's keep in mind that c is the hypotenuse, also known as the longest side in a right triangle. Okay, so c we're going to treat as the longest side of the triangle. But there's a test that some of you might be familiar with where you could just see, what happens here. Because if it's the case that it's a squared plus b squared, and that ends up being greater than c squared, what that's going to give you is an acute triangle. All right. Whereas this is a right triangle. This would give you an acute triangle. And the last remaining scenario would be such that a squared plus b squared are less than c squared. Well, that would give you an obtuse triangle. Now, this might be difficult to memorize. I mean, this green one's easy enough to memorize. Most students have dealt with this a lot in their life, probably, right? Pythagorean theorem. A squared plus b squared is greater than c squared, and this yellow one here might be a little less obvious. I like to think of it this way. The bottom line is, imagine you had a right triangle, okay? And as we know, this is the hypotenuse, that's the longest side. Okay, so that's C, okay? The way that I like to remember it is, if you look at this yellow one in particular, and you imagine that C squared is greater than this stuff. So that means that C squared is really big, okay? C squared is big. And that's the way to think about it, and therefore C is big. So if you think about that, in my opinion, it becomes a little bit easier to remember. You can imagine that C got bigger, right? With exclamation points. C is bigger, which turns this, what would otherwise be a right triangle, it morphs it into this obtuse, sort of stretched out situation. And this, what would otherwise be a right angle, becomes an obtuse angle. Okay, so in my opinion, that's the best way to remember it. And if you could remember that this is true of this scenario, then this one is the only other remaining option, meaning it's acute. Okay. So that's sort of a mental trick to just remember what's happening. As it pertains to this problem, however, we have 4, 5, and 7. 7 would be your C, because 7 is the longest side. And as I said, we want to put it to the test. We want to find out, what is this symbol? Is it equals? Is it greater than? Or is it less than? Well, what we're going to do is we're going to fill it out with the numbers that they gave us. Now I'm going to use empty parentheses for now. And like I just said, it's definitely going to be 7 here. We also have 4 and 5. And we're going to sort of figure it out. We have 4 squared, well, that's 16, plus 5 squared, well, that's 25. I'll still do the underline. And then we have 49 over here. 16 plus 25 is 41. Now, what we can see clearly is that 41 is less than 49, and therefore we're dealing with this situation, and therefore it is obtuse. So it's going to be scalene obtuse. We already knew it was scalene because all the side lengths were different, and we just found out that it's an obtuse triangle, therefore it is a scalene obtuse, and that is answer choice H. When a math problem asks you to find the domain of f of x, it's often a roundabout way of saying, let's assume x can be anything except what. Okay, so that's sometimes a good way of thinking about it. Now, there's a few ways of knowing what, x cannot be. One way is to look at the graph, and they do actually provide a graph in this particular problem, so that's pretty good. So we have a graph that sort of looks like this, but it's got a hole right there corresponding with 3, and it also looks like it sort of goes up like that, so it looks like there's an asymptote here, okay? So in other words, there's something about this x value here where the graph actually won't ever touch or kind of go over this blue dotted line, and the graph on this side similarly does not go over that blue dotted line. So we know that x, the domain, which is the set of all x values that this graph covers, the domain is clearly everything except for this moment and this moment right here. Now, it might not be clear what this x value is here, okay? And in order to find that out, you have to ask yourself, okay, well, what x values would cause this function to be undefined? Okay, so the bottom line is when you have especially a rational function like this, from an algebraic point of view, you could figure out which x values are not in the domain by finding out which x values would cause this to be undefined. Well, what does that mean? That means which x values would cause there to be a denominator of 0. So when you investigate that, you realize, okay, well, let's factor the bottom and let's see what happens. So we're going to have x, we're going to have x, we're going to have x, looks like it would be plus 1 and x minus 3. So we can see that if x was a negative 1 or a positive 3, I'll just write that. If x equaled that, the function, I'll say then f of x, would be undefined. Would be undefined. I'll just write that for now. So the bottom line is we know that if x was negative 1 and x was positive 3, well, this would be a denominator of 0. Therefore, it would be undefined. And therefore, these x values cannot be in the domain. Well, we already figured out that the x value of 3 can't be in the domain because there's a hole there. We already knew that. But what we didn't know, what wasn't as obvious, was that this asymptote happens to be at the x value of negative 1, okay? And that is confirmed at this point, okay? That is confirmed now that the asymptote's at negative 1. So the truth is that x could be anything, or x is anything in the domain, except for negative 1 and 3. Because if x was negative 1 and 3, then the whole function would be undefined, and that's not allowed, okay? That's the way to handle that. Now, the next question is, what the heck is going on with this terrible notation? Okay, so I'll just tell you right now, the answer is J. And here's the notation they give you. Okay, and I'm going to just translate what this means real quick. All right, the and symbol like that. We have x does not equal. Okay. Okay, so I'm just going to translate this sort of math language here. What this says is the domain is all x values. So x could be anything. And this usually means such that, okay, or given. We could say given. Okay, it's kind of related. So x is anything given that x is not negative 1 and not negative 3. Okay, so x is anything given that or such that x is not negative 1 and x is not negative 3. Well, isn't that what we just discovered? Okay, that is what we just discovered. So that's that. Now, some of you might be wondering, well, what about if we could cancel these? Does positive 3 still count as one of the values that x is not allowed to be in the domain? If you cancel these, because that could reduce to 1 over x plus 1 after canceling these, it would reduce to 1 over x plus 1. And the answer is it's still the case that because at some point in time before the cancellation, the denominator was represented thusly, and thus could be factored like this, because at one point in time this was the denominator, it still remains to be the case that x is not allowed to be 3 because it would be undefined, okay? And when it is a cancellation scenario like that, it turns out to be a hole rather than an asymptote, that's all. But the bottom line is x still can't be 3, okay? So the presence of the hole is all you need to know that 3 is not included in the domain, and of course, similarly, negative 1 is not included in the domain. Okay, so that's sort of beyond the scope of what you need to know for the ACT, the fact that it would be a hole rather than an asymptote. But the bottom line is, even if you could cancel it, the fact that this was here at one point in time means that 3 would cause the whole function to be undefined, and therefore 3 is not in the domain. Problem number 52 requires you understanding a little bit more of a formal definition of what a circle is. And a circle is essentially when you have a point and you call that the center. And then you say, okay, there's a radius of, I don't know, 10 or something. And, you just imagine all the points that are 10 units away from this red center point. So again, I'll sort of rephrase that or restate that. A circle is all the points 10 units away from this center point. Or we could say this circle is that. So here's a point that's 10 units away from the center point. Here's a point that's 10 units away from the center point. Here's a point that's 10 units away. Here's a point. Here's a point. Here's a point. Here's a point. And I think you see where this is going. Wouldn't that turn out to be a big old circle, right? If you connected all the points. So that's sort of like a formal definition of what a circle is. It's all the points that are a certain, you know, amount of distance away from a center point. Okay. So that's one way of thinking about it. Now, let's investigate problem number 52. Apparently, the center is 1, 3, and apparently the circle passes through 4, 7. Okay, 4, 7. So maybe it's helpful to just sort of at least draw a rudimentary graph that would highlight what's happening. So we have a center here at 1, 3. We have a point apparently on the circle, that is at 4, 7. So that's going to be right there. So we can imagine that this certainly goes all the way around, right? So when looking at answer choice, let's say F, it says 5 coordinates. We could say the circle centered at 1, 3 that passes through 4, 7 is the set of all points that are, let's investigate the first answer choice, 5 units from 1, 3. Well, is it the case that a circle, this circle is 5 units away? All the points that are 5 units away from the red dot. Well, let's investigate it by figuring out, well, what is this radius here, right? What is the radius? And some of you might realize very quickly that you could totally use the distance formula for that, okay? Now, the distance formula, in my opinion, would be a smart idea for you guys to know for the ACT. All right, and here it is. It's often the case they do x2 minus x1, y2 minus y1, so we're just going to kind of stick with that. This will be x1, y1. This will be x2, y2. Now, once again, this big ugly thing will give us the distance between these 2 points because that is the radius, right? So going through the motions, we get, that would be 1, or 4 rather, minus 1 squared plus, that would be 7 minus 3 squared, and that ends up equaling 3 squared plus 4 squared. That ends up equaling 9 plus 16, and then of course we have radical 25, or the square root of 25, and that is most definitely 5. So apparently this radius is 5. And that is exactly why the answer to this one is F, answer choice F, because turns out the radius is 5, and therefore F gives us a proper description of what's happening, or how to define this circle. The circle could very easily be defined as the set of all points that are 5 coordinate units away from 1, 3, which is the center point. So the answer, once again, is F. What a weird problem 54 is. It could be the case that you've just never seen a problem like that, So these graph type problems where you're analyzing the real world and all that, and what the graph would look like, well, yeah, you unfortunately have to really think about what's happening in the real world, okay? So I'm not going to worry about the exact like numbers involved just yet. But let's just say here's a graph that says this is the amount of like copies that are being made. This is the time gone by. Now, when copies are being made at a fast rate, then that's going to be a lot of copies for a small amount of time, which would give us a steep slope, right? If it's the case that the speed at which copies are being made slows down, well, then the slope is going to get less. That means more time is going to go by with less copies being made, okay? I think that's a good insight to begin with this problem. Now, the bottom line is, when you look at the paragraph, what you learn is that everything was going normally until 10 a.m. Okay. 10 a.m., weird stuff started to happen where, like, at least one of the things broke, right? And then it got back in service later. But at 10 a.m., things started to slow down because one of the machines broke. And you know what else happened? At 12 p.m., um, another thing broke. So, and then that thing got back to normal at 3, right? So, what we know is between the times of 10 a.m. and 3 p.m., regardless of which machine had broken, whether it's machine A or machine B or whatever, between these two times, things were breaking. Okay. So, the amount of copies we're slowing down between these times, okay? Again, regardless of which, machine it was, we know that bad things were happening between 10 a.m. and 3 p.m. So it makes sense that you'd have a graph where everything's going normally, but then somewhere between 10 a.m. and 3 p.m., it just kind of slows down a little bit because there's still always this one copy machine that's still copying. But things slow down, right? So the slope gets less steep, right? Slope gets less steep. But then once they fix it at 3 p.m., it goes back to normal again. So the point at which things started slowing down should be at 10, and the point at which things got back to normal, should be at 3. Okay. And the only graph that sort of denotes that situation is answer choice F. Okay, answer choice F. Now, let's see, let's look at G. Now, G has things going wrong around, no, G actually has things speed up at 10. So that doesn't make any sense. G says that it started slow and then the copy sped up at 10. So that's wrong. That makes no sense. Answer choice H, we could look at that. Yeah, that's wrong for the exact same reason. Okay, that's wrong for the exact same reason. Looks like things speed up after 10. Answer choice K doesn't work because that assumes that there was a steady amount of copies being made the entire time. And answer choice J doesn't make any sense because the bottom line is over time, there were still an increasing amount of copies being made, if for no other reason than the fact that there was at least one machine functioning the entire time. So there should be this continuous movement upward throughout. Okay, so answer choice J does not make any sense. Answer choice F is where it's at. It really just requires getting clear on the big picture. From 10 a.m. to 3 p.m., things should basically have slowed down due to the fact that machines started breaking, and then everything was fixed by 3 p.m. and things got back to normal. Sometimes I think it's helpful to get a visual of what's happening. So what we have here are banners that are composed of a blue piece and a white piece. We'll just sort of put it that way. And let's imagine that this is the banner right here, and the blue piece is right here. Okay, now this is not drawn to scale, but it's just to give us a basic idea of what's happening here. So the blue part is apparently 1/4 yard. And this white part here is apparently 3/8. So that's one single banner, and we're looking for 500 of these, essentially. Now, of course, there's more to this problem. There's mention of the fact that they decided to go with 10-yard bolts of blue material and 12-yard bolts of white material. Now, we can get to that in a moment. Okay, we can get to that in a moment. However, in the meantime, I think what would be smart for this problem is to just be clear, okay, well, how many, you can think of this single banner. This is a single banner. And really, since the problem moves into, 10-yard bolts and 12-yard bolts, right? Length is something we need to be taking into account, all right? My question is, if each of these blue blocks is 1/4 of a yard, what's the total length of 500 of these? Because we need 500 of these banners, but let's focus only on the blue portion. What would be the total length of just the blue material if it's the case that we're looking for 500 of these? Well, that would be easy. That would just be 500 times 1/4. Since there's going to be 500 of these blue blocks, if we want to know what the total length of the blue material would be, well, it's going to be 500 times 1/4. So we therefore know that the total length of the blue fabric, or whatever it would be, is going to be 500 times 1/4. And that turns out to be 125. That's the total length of the blue material. Then we have the total length of the white material to contend with as well. Well, similarly, that's going to be 3/8 times 500 because this is a full banner. Each banner has 3/8 yards of white material. If we want to know the total length of white material for 500 of these, well, it's going to be 500 times 3/8. So we could say the total length, I'll use the word length here. We should probably make that clear. Total length of the white, that would be 500 times 3/8. And that turns out to be 187.5. So that's that one. That is important information because they then tell us that this organization is going to be purchasing 10-yard bolts of the blue and 12-yard bolts of the white. So the question is, if what we need, the question at least for now is, if what we need is 125 total yards of blue, and you are purchasing blue in 10-yard bolts, well, how many of those bolts would you need to purchase? Okay, well, that would be 125 total yards divided by 10. Okay, because we need 125 total yards, and we're purchasing 10-yard bolts. So to find out how many bolts you would need, you'd have to divide that by 10, and that would give you 12.5. Now, in the real world, we're not buying 12.5 bolts. Bolts don't come in half sizes, probably. So you'd probably have to buy 13 bolts in order to ensure that you have enough. So that's that one. That at least gives you that information. We're going to need 13 bolts. Now, let's do the exact same process to figure out how many bolts we need to purchase for the white part. We know that we need 187.5 total yards of white in order to make 500 banners. We're purchasing the white material in 12-yard bolts, so many of you watching probably understand that we'd have to simply divide 187.5 by 12, and that would give us 15.625. Similarly, we will have to round up to make sure that we have enough material. So we would need 16 total 12-yard bolts of white material. So now let's find out how many actual yards of material did we just purchase? I mean, we know that we got 13 bolts of the 10-yard material, and we know that we got 16 bolts of the 12-yard material, right? It's a little tough getting all the numbers straightened out. Once again, this represents bolts, so we'll just write bolts there. Let's make that clear. And this is blue, and this is white. So we're going to get kind of specific just to make sure we understand what these numbers mean. So how much length would this be? Well, this would be 13 bolts times 10 yards, because each bolt is 10 yards, and that would give us 130 yards. So that would give us 130 yards of blue. Similarly, what would the total length be of 16 bolts of white? Well, each of these bolts is 12 yards, so that would be 16 times 12, which is 192 yards of white. That's what we would actually have after purchasing 13 of the 10-yard bolts of blue material, and after purchasing 16 bolts of the 12-yard white material. We'd have 130 total yards of blue in our possession, and we'd have 192 total yards of white. That's what we would have actually purchased. So then the question is, that is more than we need, and you can really see that. I mean, we now have 130 yards of blue, when the truth is, for 500 banners, all we needed was 125 yards. We now have 192 yards of white, when the truth is, all we needed was 187.5 yards of white material. So the question is, what or how many extra banners can we make, given the fact that we have this surplus here? Well, the trick is you need to be very clear about what the difference is between 130 and 125, and what the difference is between 192 and 187.5. So what we're going to do is we're going to say 130 minus 125. Well, that's going to give us 5. So we have 5 extra yards of blue. And over here, it's going to be 192 minus 187.5. 192 minus 187.5. We have a 0 there. That's going to be 4.5 extra yards of white. Okay, we can say extra yards here. So how many total extra banners can we make? Well, we're limited by this smaller difference. Okay, we're limited by this 4.5 here, because the bottom line is we need to find out, okay, this number is smaller than 5, so this sets the parameter of how many extra banners we can make. So we need to focus on this number. The question is, how many extra, how many white blocks that are each of length 3/8 can we fit inside 4.5 yards? So I'll say that again. How many of these 3/8 white blocks, each of which is 3/8 of a yard, how many of those would actually fit inside 4.5 extra yards of white material? Well, all we'd have to do is divide 4.5 by 3/8, which is really the same thing as multiplying 4.5 times the reciprocal. And that turns out to be 12. So we can fit 12 of these white blocks, each of which is 3/8 yards. We could fit 12 of these white blocks within the 4.5 extra yards of white material. Now, just to be thorough, let's find out how many of these 1/4 yard blue blocks could fit inside the 5 extra yards of blue material. It would be the same process. It would end up being 5 divided by 1/4, and that would be 5 times the reciprocal, and that turns out to be 20. So we could definitely get 20 of these blue blocks, but 12 is less than 20. So as I sort of hinted at and suspected before, we're really limited by this smaller number here, okay? It's really this number. We're limited by the fact that we can only get 12 extra white blocks with our extra material. And sure, we could get 20 extra blue blocks within the 5 extra yards of blue material. But the bottom line is, we want to know how many extra banners we can make, and the banners require both white and blue. So we're limited to 12 because there's only 12 white blocks within our extra material. So hopefully that makes sense. We're limited to 12 extra banners, and that is the answer. The answer is answer choice A. So unfortunately, problem number 58 is somewhat time consuming. Not only is it somewhat time consuming because you're going to have to multiply x minus 3i times x minus 3i times another x minus 3i. It's time consuming in that way, but also you do, of course, have to be careful with the imaginary number I. Now, very quickly, you want to treat the imaginary number I like a normal variable, all the way until you get to the very last move of solving the problem or simplifying the expression. So in other words, 3i plus 5i would be 8i. You also need to remember that I squared equals -1. And when you kind of work the problem out, after having treated I like a regular old variable, in the very last moment, you want to just scan what you came up with for any I squareds and turn them into a -1. Okay, so that's the important thing you need to remember. Beyond that, this is really just a FOIL problem or just really a multiplication of different quantities problem. So the truth is that x minus 3i cubed, well, that's really x minus 3i times itself, and then times itself again. So that's the reality of what we're dealing with here. So rather than think about this, I'd rather focus here. And what we're going to do is we're going to focus on just 2 at a time. At first, we could really just think about what's happening here. Many of you watching know about FOIL, first, outer, inner, last. Well, that's what we're going to do with these. What I'm going to do, furthermore, is I'm going to wrap these in green brackets because I want to make very clear what this becomes on the next line. After foiling it, we end up with x squared, that's first times first. Then we're going to have outer times outer. That's clearly going to be negative 3ix, which I know is weird, but if you think about it, that's true, right? 3ix. Now I'm keeping the x on the right-hand side because the truth is that it's kind of better to think of I as just a number at this point. And x is the variable, and usually you put the variable, to the right. When we do inner times inner, well, it's going to be the same thing. It's going to be negative 3ix. And then the last times last would give us a positive, you got to be careful, 9i squared. Some of you might be looking at that I squared and thinking to yourself, -1. And you would be right, but we're going to worry about that stuff at the end. I'm going to wrap this in brackets because this is still sort of its own quantity. And this is the result of having worked out this part. But we still have this on the outside, don't we? So we're going to write that on the outside. There we go. Now we have some simplifying to do in here because these two combine and turn into a -6ix. So on the next line, we're going to go ahead and just do that. Now I'm just going to drop the green brackets because I think it's clear that this whole thing inside the green brackets is the result of the work that we did here. So x squared minus 6ix should be in parentheses though, plus 9i squared times x minus 3i. Now I'm actually seeing that, believe it or not, now would be a pretty good opportunity to turn that into a -1 because when we multiply this 3i times it, which we're going to end up doing, we're going to have an I cubed, and that might be just a little confusing to think about. I mean, it's something that we could work with and figure out what that is, but that'd be a little bit more confusing, whereas right now, we could just simply turn that into a -1. So I'm going to do that right now, just to kind of nip it in the bud right now, okay? There is like a whole thing where you maybe even memorize what I cubed is, but we'll keep it simple. So we have x squared minus 6ix, and that's going to be -9. And that's going to be times x minus 3i. I'm a big fan of remembering the pattern. We have a binomial times a trinomial. And the question is, what do you do when that's the case? Well, imagine you have a binomial, just do these little placeholders, and a trinomial, and you're trying to multiply them. Well, all you need to remember is that it's going to be this little guy times all of these, and then you're going to add that, or combine that with this one times all of these. So if you could just remember that sort of pattern where you apply this one to everything, and then you apply this one to everything, and then you just simplify all that. So that's exactly what we're going to do here. So when it comes to x times x squared, well, that's going to be x cubed. Then it's going to be x times -6ix. That's going to be -6ix squared. Then it's going to be x times that -9. That will most definitely be -9x. So now we are ready to apply this -3i. -3i times x squared would be -3ix squared. Then we're going to have -3i times -6ix. Well, that's kind of an interesting one. First of all, it's going to be positive. -3i times -6ix, that's going to be positive. So you just put a plus sign. And then it's going to be 18i squared x, right? If you have to pause the video and think about that one, feel free. Then we have -3i times -9. Well, first of all, that's going to be positive. So it's going to be plus, and then we're going to have 27i. So let's take a look at this. I mean, we have an x cubed, that's the only x cubed. We've got an x squared here. We've got a like term, so these two are like terms. We're probably going to have to combine those. That I squared is going to turn into a -1. So that's going to turn into a -18x, which is going to make that a like term with this -9x. So we're just kind of getting a feel for what's going on. In my opinion, probably the smartest thing to do at this point is to actually just go ahead and turn all the I squareds into a negative. And then I think we'll just have a clearer picture of what to do. And when I say negative, I mean -1. So we have x cubed minus 6ix. Nothing changes about that. Minus 9x minus 3ix squared. Now here's the tricky part. Remember, that turns into a -1, so that's going to be a -18x. And then plus 27i. So at that point, we can very clearly see that we have x cubed. We have a like term pertaining to ix squared, these two. That's going to turn into negative 9ix squared. Now already, you should see that the answer is either going to be f or h, or rather, well, it looks like it's just f actually. I think we're done. Okay, I think we're done. I could simplify all this stuff, okay? But the only answer that has x cubed and a negative 9ix squared is answer choice F. All right, now I promise you, if you were to proceed with simplifying the rest of this stuff, it would be answer choice F. And you can feel free to do that if you want. Just make sure it matches answer choice F. But part of the ACT is saving time. So we just did that. We just realized, okay, blah, 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 blah. And then all of a sudden it's like, oh, the only answer literally that has this in it is answer choice F. Done. So what we have on our hands here is a question that, in a way, challenges us to understand what's happening between a graph and the factored form of a polynomial function. I'm going to present to you an example that is not the same as the problem, but I want to give you a simple example to sort of illustrate what's happening. And here it is. We have this, and we have this right here. So imagine this is the function. Well, the truth of the matter is, we know that this function has zeros at -3, -2, and +2. So that means at -3 and at -2 and at +2, this graph intersects the x-axis. Now, that makes total sense because any point on the x-axis has a y-coordinate of 0. Any point on the x-axis has a y-coordinate of 0. So if you imagine that x was -3, well, that would be -3 plus 3, and that would be 0, and it would be 0 times this whole thing, which would make the y-coordinate 0. The same philosophy applies to these factors as well. So we know for sure that there is indeed, or are indeed, zeros at x equals -3, -2, and +2. I'd like to draw your attention to this exponent of 2 and this exponent of 3. When it's the case that you have an exponent of 2, that means that the 0 that's associated with this factor, the 0 that's associated with this factor, in this case it's -2, that represents a double root. And what that means is the graph grazes the x-axis. Now it does intercept it, but it doesn't go past, it goes down again. Okay, at least in the case of this function, it would go down. So when there's that exponent of 2, the graph grazes that 0 without going past it. When there's an exponent of 3, the graph grazes this 0, or that 0, but then kind of slides over and goes up. So what do I mean by that? I'll just kind of draw the graph. The graph here would be this. Remember, the double root means it grazes it, but then it goes back down again. And then over here, it kind of grazes and slides through, but then goes up like that. So basically, for this particular problem, the ACT is quizzing your understanding of that. Okay? I don't know if quiz is a verb, but I think you get what I'm saying. So that's how that works. Now, I'm going to draw the graph from the actual problem. So here's the graph from the actual problem, to the best of my ability. Well, first of all, we know that there's three zeros. There's a zero at -4, a zero at 0, and a zero at 6. So I'm actually just going to use y instead of the function notation here. And we know that there's three factors because there's three zeros. This factor here is associated with x plus 4. Okay. This factor here is associated with x minus 6. And this factor right here is associated with just x. Okay. Now think about that one. If x was 0, then y would be 0. Therefore, the point 0, comma 0 is on the graph. I'll say that again. If this x is 0, it would make this y 0. Therefore, the point 0, comma 0, the origin, is on the graph. Well, there it is. Okay, now it looks a little bit off to the side, but you understand. In the actual test, you can very clearly see it intersects the origin, 0, 0. So that's why the 0 associated here is actually just x. Okay, now this is a double root. The fact that it goes up, grazes, and goes back down, that means it's a double root, which means that we have to put that exponent of 2 hovering above it for all the previously mentioned reasons from that other example. This is that sliding motion. It goes through 6 and then it goes up. Well, that's the cubing action that I had mentioned before, and that's associated with this factor. So that's that. I mean, this is this at least very, very well could be the function denoted by this graph, and that corresponds with answer choice D. Now, D is written in a slightly different order, where answer choice D says x squared times x minus 6 cubed times x plus 4, so slightly different order. But as you all know, multiplication is commutative, so therefore it doesn't really matter what order we list these, it's still just multiplication. So that is how you do problem number 59. The answer is D.